Okay, it's 12 o'clock, so welcome to another installment of Polish NMR seminars. Today we have both speakers from Mickiewicz University, from NanoBioMedical Center. We start with Weronika Wrembel, then we'll have the Dr. Tomasz Zalewski talk. But first, as usual, few announcements. Just So we continue with best student question competition. So we encourage students to ask questions. The winner of each semester will get some nice Polish Chemical Society gadgets. Also, in 2 weeks and few days, we see each other in Warsaw in Polish NMR meeting. We have 89 people registered. The program is already on our webpage. So see you all within 2 weeks and few days. And we go back to the talks. So first talk will be by Weronika Wrembel from NanoBioMedical Center at Mickiewicz University, and she will give us a talk titled Temperature-Dependent Molecular Dynamics of Imidazolium-Based Ionic Liquids Studied by NMR and DSC Methods. So Weronika, the screen is yours. I just switched off the sharing.
Yes, thank you very much for the introduction. Do you see everything?
It's loading. Now we see it. Yes.
Okay. So I would like to tell you a little bit about my work. My topic is temperature-dependent molecular dynamics of imidazolium-based ionic liquids studied by nuclear magnetic resonance and differential scanning calorimetry methods. Wait a second, because something is not working. Okay. First, substances that I'm investigating are from the group that is called ionic liquids. They are defined as chemical compounds with an anion structure and melting point below 100 degrees Celsius. And this is most due to the significant size difference between an organic bigger bigger with extensive alkyl chain cation and a small organic or inorganic anion. And this is hard for the system to form homogeneous crystal lattice. And they are characterized by unique properties such as high thermal stability, low volatility, and there is a great use, a great interest in their use in great chemistry, for example. So now on the screen, you can see substances that I'm investigating. I divide them into two groups. The first group, they are with the BF4 anion, and the second group, they are with the chlorine anion. And inside each group, they differ by their length of the alkyl chains. And the goal is to investigate their molecular dynamics and compare them together and see how the structure affects their properties. So now for the measurements, first the substances were prepared by cleaning and drying them chemically using the method of freezing and sublimation to get rid of any water and solvent vapors inside them, using a two-stage system in the oil pump. And for the methods that I want to present you, first method is are the nuclear magnetic resonance experiments. First experiments were performed on the 200 megahertz spectrometer for the hydrogen 1 atoms and the fluorine 19 atoms. And then the experiment was carried on the 25 megahertz spectrometer for the hydrogen 1 atoms. All of the experiments were carried in the range of temperatures from 80 to 350 Kelvin. The second method is differential scanning calorimetry. which was performed from 150 to 405 Kelvin with the speed 10 Kelvin per minute. And the last method that I will talk to you about is the continuous wave NMR from 75 to 330 Kelvin. And now for the results. Here on the top row, we can see the thermograms for the substances from the first group with the BF4 anion. In all of those graphs, there are clearly visible two phase transitions. The first one is a glass transition, and the second is the melting-like process. For of the phase transition, we estimated the onset and temperatures and calculated the enthalpy. And comparing them together, we saw the connection between the length of the chain and the temperature. The longer the chain, the higher the temperature of the transitions. And on the lower part of the screen, we can take a look on the graphs. On the graphs, we have the relation of T1 relaxation time values and the relation to temperature. The temperature is shown in the reciprocal scale of temperature. So here we have the low temperature and here we have high temperature. And the results were interpreted using the BPP model, which is the Blomberger-Pound model, which is the model that is usually used to describe the behavior of methyl groups in the system. We have two methyl groups in the system, each one on the different side of the alkyl chains. And we using the model, we fitted the exponents to find the methyl group motion. We can see the fitting as the dotted curves on the screen. And we concluded that we have in lower temperature. So here on the graph, we have two separate methyl group motions, which is anisotropic axial rotation of the methyl group in low temperatures. Then in the range of temperatures between two phase transitions, we have the most dominant process is conformational changes of the CH2 groups. And in high temperatures, we have some overall motion. So as you can see, the graphs look pretty similar. In each case, the motions are similar. And we can take a quick look at the graphs for the systems with chlorine atom. They are also, we have two phase transitions. We have also two rotations of methyl group, but they are the temperatures are slightly different. And we can see, looking at the thermogram, that the system with the chlorine is much less stable because we have some degrading of the chlorine in the high temperatures. Then the second experiment was performed on the fluorine 19. We wanted to check if the alkyl chain length between those three systems with BF4 has an impact of the behavior of the BF4 group. But all of for those substances, you can see that the graphs look nearly the same. So it's pretty much no difference. So we can now see the another slide, which is comparison between the T1 relaxation time values from the 200 megahertz and 25 megahertz spectrometer. This is the first experiment, the black dots, the 200 megahertz, and the red dots. We can see the 25 megahertz results. we can see that the minima are shifted to the lower T1 values and slightly to the lower temperature. It's accordingly to the theory of relaxation. We are still working on fitting them together on one graph to better show the results. And the last experiment that I would like you to show you is the continuous wave spectroscopy. We are still working on this experiment. We measured the first derivative of the absorption spectrum, and from this we calculated the second moment, which is shown on the top graphs, and the delta H, which is line width on the bottom graphs. And looking at the second moment, we can see that we have a slope, different angle of slope, and we can interpret it this that in the molecule we have motion, and the motion is increasing its speed. And what is worth to add, we can see in the delta H values, there are some sudden drops of the values, but here we have in some cases they increased. So we suspected that it could be related to some dynamic ordering in the system, but it's still under investigation. So for conclusions, we have two different types of phase transition in each of the systems. We are sure that we have anisotropic rotation of two individual methyl groups in low temperature in all of the resistance. And then conformational changes of the CH2 groups and slightly higher temperatures. And for the repetition of these processes, for the BF4 anion systems, the processes are fully repetitable, but for the chlorine, we have very less stable system, and we cannot repeat it with the same effect. And we think that we have the amorphous character of all of the system, but we are still investigating and trying to connect all of the results together and make some more measurements to get a better, fuller image of those systems. So yeah, thank you very much for the attention.
Thank you very much, and we are open for the discussion. If you want to ask questions, please turn on your microphone and if possibly camera. If you're a student and you want to take part in the competition, remember to have your full name in the Zoom or introduce yourself. So we are open for discussion. Anyone? Okay, so maybe a starter question from me. When you were comparing the 25 and 200 megahertz
Yes.
results, did both have the temperature calibrated, or this is just the information from the system?
We change manually the temperature in both of them, and this is the information from the system.
Okay. And what was your temperature rate, out of curiosity, like
From
switching
80
between-
Kelvin to 350 around, because in the megahertz we had some problems with really low temperatures and really high temperatures. So the range is around 80 to 350, but in some cases, as you can see, we have some difficulties. Yes.
Yeah. And how fast were you switching?
I think we were waiting around 15 minutes to the temperature to set, and then we performed the next measurement.
Okay, thank you.
Thank
Anyone
you.
from the audience? Give it a moment. Okay, doesn't look like. Okay, so thank you very much, Weronika. And we switch to another talk from Tomasz Zalewski. So stop participate sharing. Okay, so the next talk will be titled Development and Investigation of Modern MRI Contrast Agents. And the screen is yours.
Thank you very much for the opportunity to talk. I just want one comment with Weronika. It's from Department of Physics at Mickiewicz University. I think it could be important for someone.
My mistake. So I switch it in the web page.
Yeah. Okay. So today I want to show some results about cooperation of the laboratorium of magnetic resonance imaging with the people from from the NanoBioMedical Center where I'm working, and I want to show some information about the development and investigation of the contrast agent for using in MRI experiments. So why we choose the nano, because nowadays we are living the nano time, so it's every one of you knows that the nano is 10 to the minus 9, but the nano is a very fancy word today, so we could find the nano shops on the street, and also we could buy a lot of nano things, for example, to paint our wall. And of course, if we want to protect our surface, we want to find the nano coating spray. So nano is everywhere, but the people really looking for something different. They looking for the nano robot. They want to create a nano robot, especially from the medical point of view, which could help protect our health, and in some reasons help to make some surgery inside the body. But to get the nanorobots, first of all, we have to create the nano object and trying to understand how the nano object works. So the main aim is to project a new multifunctional nanocarriers. What this means, the new multifunctional, it means that the nanocarriers have more than one function. So not only a carrier, not only a contrast agent, but at least two functions together. From my point of view, we want to assess the relaxivity properties of nanoparticles, and we want to know that there is useful for us to use them as a MRI contrast agent. I suppose that most of you know what is the contrast and what for we're using a contrast agent, just to recall. And in the MRI experiment of NMR experiment, a contrast agent should have some magnetic properties, and the most popular one is paramagnetic. So we are using in clinical a lot of paramagnetic chelates. And also we could using paramagnetic salts when we prepare NMR experiment and we want to make our relaxation time shorter. And of course, because of nanotechnology allow us to create some nano objects, we could help us to create a nano object. So for example, we could create a super paramagnetic iron oxide, which offer a very high contrast, especially influence very hardly in T2 because of very huge disruption of magnetic field. And we have a third model where the diamagnetic, when we are saturate some, for example, proton, and the proton exchange with a proton we are not saturated, and we could observe the chemical exchange saturation transfer. It could be useful especially in the medical experiment. In our work, we are working with paramagnetic contrast agent, and to get some results, to assess them, we are using a quite standard method, of course, inversion recovery sequence. But if we want to get information in a wide range of the magnetic field, we could use it, for example, a field cycling method. And we have two options. The first, we have a pre-polarization, and then we are relaxate in the lowest magnetic field, or we have a relaxate function. We put it in the magnetic field, and then we are make experiments. And from this data, we could of course get also T1 in the low magnetic field. From this T1, we could obtain the relaxivity parameter. What it means that we have a relaxivity rate, and we could observe how the relaxivity rate is dependent of the concentration of the, for example, paramagnetic ion in our sample. So we got something like this graph, and then we are fitting it in, and the value R is taken from this fitting line. Okay, why we want to create a new contrast agent? This is a graph of the contrast agent using in the clinical application, and we could observe that the relaxivity is quite high in very low magnetic field. But nowadays we are using in the hospital the magnetic field from the 0.5 Tesla to 3 Tesla, but usually it's a magnetic field 1.5 Tesla. So the value of the relaxivity from the traditional gadolinium-based chelate is quite low, and its situation even worse when we want to working with preclinical scanner like this one, which is located in our center, is 9.4 Tesla. But the preclinical study, we could also measure in the highest magnetic field. We also have some we have also have imaging system in the 600 megahertz system, so it's even worse relaxivity rate, especially in the R1 in the high magnetic field. So we want to create something will be better could be used in the highest magnetic field, because higher magnetic field offer us, of course, highest sensitivity and in some cases a highest resolution of our medical images. Okay, so back to the nanocarriers. All the nanocarriers we want to assume and we want to investigate in the two ways. The first way is the first step is a synthesis. So we are my colleagues synthesis different type of nanoparticles. It could be a core shell nanoparticles. It could be also some nanotubes with the magnetic core. This is a ferromagnetic core. And of course, we are working also with some soft matter. And for example, from liposomes, we have a liposome. There is put some active substances between the bilayer. When we accurate this, the nanoparticles, in next step, we have to carry on the physical-chemical analysis. Of course, we want to know that we curate what we want. So we are using a Fourier transport IR method. Also, we could use, in some case, the high resolution NMR. It of course depends that our nanoparticles have some magnetic properties or not. We of course want to know that we could have some fast transition in the temperature close to the body temperatures, because in some case it could help us, in some case it could be a disadvantage for our particles. And finally, we are using electron microscopy to check that we have this composition which we want, and of course to measure the dimension of our nanoparticles, especially when they are very, very small, so about the 3-5 nanometers. Of course, we are also, if there is a crystalline nanoparticles, we want to have to check that it's really a crystalline, and then we want to check that these nanoparticles are magnetic or not. If the nanoparticle is magnetic, we are very happy because we could trying to investigate them as a potential contrast agent. And parallelly, we want to check that we have additionally properties, for example, a fluorescence or different one, because our nanoparticles should be multimodal. So we want to have more than one properties inside the nanoparticles. When our nanoparticles are good and we know that they have some magnetic properties, we make a third step. It's parallel biological investigation. We want to know that our nanoparticles are safety, so we could use it in biological system, and we have to measure the relaxivity parameter of checking that the MRI contrast properties exist. And now I want to show you some examples of nanoparticles. The first one, we have core shell nanoparticles. First, we create a core. The core was created from zinc oxide doped by the gadolinium ion to give them some paramagnetic properties. And then we prepare a shell, and finally shell was a ZIFT-8, which could help us to make it as a good carrier for example, for drugs or for another active substances. And to confirm that we observe a core shell structure, we of course make a micrography of our nanoparticles. Okay, so back to our core. We adopted our core with a different amount of gadolinium, and we observed that the gadolinium is very good connected to the crystal lattice, but the line in XRD is moving up to 5% of gadolinium. When we goes to higher value, the situation is going worse. So we decide to using a 5% gadolinium doping our core. So we investigate the magnetic properties, and we observe that the best magnetic properties, the paramagnetic properties, we observe for the zinc oxide doped by the 5% of gadolinium in the room temperature. So we decide to carry on some NMR relaxation experiment, and we got a quite nice value of relaxivity rate measured in the low magnetic field. It's a standard magnetic field when we have usually quite where we in which one we could assume that our nanoparticles or our substance could be a potential contrast agent or not. And of course, we also observe the biological properties, biotoxicity, and for the cancer cells, our properties are good, and there is quite nice it looks, but the situation a little bit worse for the normal cells. But we put our shell, and our shell, of course, definitely change our active surface, and definitely change the volume where we connect some active substances. But unfortunately, the magnetic properties going worse. So we are, of course, trying to check what is the influence on relaxation, and also the result for the relaxivity parameters is worse. So for solo core, we have a 7, but for our core shell structure, we have around 2. So it's lower than the Magnevis as standard using a contrast agent in the imaging. Unfortunately, also biological properties were very poor for the core shell structure, that they shown us some information that even if we have a good core with very good properties, could be very nice use or could be potentially be used as a contrast agent, we have very careful create a shell, because not all the materials has biocompatibility like a zinc oxide. The second system which I want to show you is the liquid crystalline nanoparticle, which was mixing, or in this system we put 2 types of nanoparticles. First one was hydrophobic manganese oxide, and the second was hydrophilic manganese oxide. And of course, in the first step, we have to assess that we have a good our nanoparticles manganese oxide, and we have to measure the dimension of the nanoparticles, and then we observe that our nanoparticles are inside our liquid crystalline, and we confirm that these are true. So we start to measure the relaxivity properties. This is just the dispersion of manganese oxide, which was hydrophilic, and in the 16.5 megahertz, the result of relaxivity rate was not very nice. But when we put it inside our liquid crystalline, the results are very nice. And we could check with a different system to recall this is manganese. So this from manganese, there was the one manganese system which was commercial available till the end of the 2010 in Europe. The results are much better than for that one, and of course, that's much better than for commercial one, Dotaran. But we not really understand why this value for the nanoparticles with hydrophobic is better than the hydrophilic one. And so we decide to carry on the 070 T2 relaxivity experiment. Of course, we have some line for the salt, manganese chlorine, which could assess that our method is good. And we got the number of Q. What is the Q? The Q telling us how many molecule is coordinated by paramagnetic center. And it's interesting because for the hydrophobic one, the Q is higher than for the hydrophilic nanoparticles. It's interesting, but it could in some ways explain why we observe the highest relaxivity rate for the system with hydrophobic nanoparticles. Of course, we were very satisfied with the results, so we are trying to make some imaging, and we got from the system just metal oxide nanoparticles dispersion in the water. The T1 weighted time are not so nice, but T2 weighted time are very good. And for this lipid liquid crystalline, we observed T1 is very high, T2 is worse. But why is worse? If you carefully observe this, the amount of the manganese is much more lower in this system than this one, which was dispersion in the water. So we still observe a very nice images, especially T1, which are very often used in the clinical application. So this is, in our opinion, the good way to working with these nanoparticles. Of course, we want to confirm it during MRI in vivo experiments. Of course, to have to find that our nanoparticles or our contrast agent is working, first of all, we have to make reference images without any chemicals add to the body. And so the first image is here, and after several minutes of the experiment, we inject in the nanoparticles suspended in the matrix gel. The first group was manganese oxide dispersion, and we observed the not very intensive T1 weighted images. So we want to observe how it looks like in the rest of our groups. So we second time have to carry on the experiment without any nanoparticles, and we observe that this is an influence of the nanoparticles. One thing which I have to tell you, this experiment is a little bit tricky because we perform the first experiment, then we have to take our animal out from the magnet, make an injection, and we carry on the second experiment. So in some case we have a little bit movement of body. So we are trying to choose the same place, but it's not so easy to make it. And the third experiment, and we observed that we believe that the effect will be the best in this way, and we confirm that this for the hydrophobic nanoparticles putting inside the layer of lipid liquid crystalline, we observe the best relaxation effect. And finally, I want to show you our longest story. It's about the liposomal nanocarriers. We start some time ago, and first we create our liposomes using a traditional film hydration extrusion method. This is some disadvantages. First one is quite big size, and second one, the active substance which we want to put inside the bilayer should be not so high like we want to have. The amount is not so high like we want to have, because the system is created in the two ways. The one is standard lipids. The second is the lipids with adding gadolinium chelate. And the third is active substances. In our case, it's photosynthesizers, zinc, phthalocyanine. And of course, we make all the steps which I mentioned at the beginning of my presentation. And we, of course, create our nanoparticles in different concentrations, especially of the gadolinium content. And we choose the one with the highest gadolinion content. We measure the size of the particles. The mean size was about 110 nanometers. It's quite okay for medical application. And we also observe that our photosynthesizer works. So in the dark, for all types of our nanoparticles, this is nanoparticles without photosynthesizers. This is nanoparticles with photosynthesizers. When we're using the light, the cell viability was very low, so our photosynthesizers work and kill the cells. The same, we observe this for the cancer cells, and we observe here the worst results for the normal cells, but still is a difference between the nanoparticles with photosynthesizer in dark and in the light. But we have to measure the relaxivity and we are really surprised that the relaxivity rate is very high. It's so high, we are not really understand what is so high, because like you remember, for the commercial one, it's about, in the low magnetic field, it's about 3. We have about 30. In the high magnetic field, we have about 10. And what is interesting, we are getting highest result from this liposomes where the zinc oxide is put in between the layer. And we are not really understand why, so we decide to make a field cycling experiment, and we observe that in the medium range of frequency, so we could call that this a medium magnetic field between 1 and 3, 4, 1 and 3 Tesla. We observe a very high relaxivity rate. We are not really understand why, so we're trying to use a modified Florence model, and we are looking for different parameters, but we are not be sure that there is because there is a quite big difference in the electronic relaxation, and it's a little bit difference in the time of life. But we not really understand what is the reason of that. So probably could be reasoned because our nanoparticle and our gadolinium could in somehow be connected to the zinc, and it influence relaxation. But we are not sure that this is true. But in first step, we have to modify our liposomes. So we are using a microfluidics method. The microfluidics method allow us to decrease the size, better, and have a highest loading of photosynthesizer. And we observed that very positive influence of this method, because viability was stable for normal cell, especially to the highest zinc phthalate concentration. And of course, we observed that this more we have phthalate inside, the loading is higher, but the loading on gadolinium is lower. But the lowest loading on gadolinium, we are not observed the influence of the relaxivity rate. So we still observe the very high relaxivity rate, even though our gadolinium content is low. So we are measure this in the low and the high magnetic field, and we still observe the difference between the samplers with and without the phthalate inside the layer. Of course, we observed that this is an influence of the active surface to the volume, and so we are sure that the microfluidics is the good way to create this type of nanoparticles. But to understand what's going on, we have to change the photosynthesizer for that one which don't have any metal. So we choose a verteporphyrin. We are trying to make all of physical chemistry analysis to confirm that we have a nanoparticles which we want to get. And finally, we are carry on relaxivity experiments. So we still observe the difference for sample without and with the phthalocyanin. It's a verteporphyrin in this type. So we are sure that this relaxivity effect is not caused, but the interaction between the gadolinium and the metal in the RF phthalocyanin. So the reason is different. So we are in the second idea. What with the reason is the difference of in the local permeability of our bilayer, because the photosynthesizer is high hydrophobic, so could change the density of the bilayer in the place it's located. So it's make the lowest density and the highest permeability in the places where it's absent of the photosynthesizer. Of course, we want to check that our system is still multimodal. So we measure the cell viability. We use a 2D model in the beginning. With light exposure, the cell viability was very high, it's almost 100%. When we start using light exposure, the viability, of course, for the sample with verteporcine is going down, and is in some way connected to the concentration of verteporcine in our system. The same situation, even if we have a better result, we observe in the 3D models, and for 3D models, we the same. Without the light exposure, we don't have any influence on cell viability. When we have a light exposure, the system showing that it's working quite nice. Okay, so if we have some nice system with high relaxivity rate, and we are sure that it could work, so we start to make a first study to observe that it could be used as a contrast agent in the high magnetic field in the MRI. So interperitoneally, we put our nanoparticles. We observe a very nice difference in contrast. So we have a high contrast in T1 weighted images. And the same we could observe in the samples when the intravenously we are putting our substances, and we still observe very positive influence on T1 weighted images. And the last system which I want to show you, we want to make them much more biocompatibility as possible. So to our liposomes, we put some PEG, the PEG to help us to our nanoparticles will be more biocompatibility and have better behavior inside the body. And we make a relaxivity experiment, and a little bit disappointing. Why disappointing? Because suddenly our additional relaxation effect disappeared, and we are not sure why. We did trying to perform the field cycling experiment, and the field cycling experiment, of course, we still have some high relaxivity rate in the very wide range of frequency, higher than for commercial one, but we not observe the positive influence like which we observe for samples without PEG, and we are not really understand why. So unfortunately, we have to back to our previous system and carry on the relaxivity experiment, because maybe it's helped us to better understand what's going on in the system from the molecular way. And some conclusion on the end. So nanotechnology based contrast agent could and usually have better relaxivity parameters than the commercial one, which nowadays using just gadolinium halates. We are very often get a very nice T1 weighted images in the low when we have a low amount of gadolinium, which made the new created contrast agent safer than the traditional ones. the multifunctionality of nanoparticles fortunately could have very positive influence of relativity parameters like in our liposomes, or sometimes could have a negatively influence like in our causal system. So we have to be very careful when we create our nanoparticles, because not all our idea could be good, but in science we have to trying to find the best options. And the last one, the analysis of field cycling profiles could help us to better understand mechanisms involved in the relaxation, which could be caused by the paramagnetic nanoparticles when we put to the system. I want to thank you to the all people which were involved in this work, especially for Beata Wedeszynska, which started working with field cycling in the liposomes, and from Natasza Babajewska, Dorota Flak, and Paulina Skupin, which was responsible for creating the new nanoparticles and make physical chemical analysis, and for rest for the team, and also for National Science Center for the financial, which helped us to realize this investigation. So thank you for your attention. And traditionally, of the end, some advertisement about the Ampere NMR School. So please join us next year in the Zakopane.
Thank you very much, Tomasz, for your talk. Yeah, of course, I fully encourage everyone to register for Ampere NMR School. It's a great event, and we're open for the discussion. So if you want to ask questions, please turn on your microphone and camera. I very encourage students to ask questions. There is something to win. So let's wait a moment. Do we have anyone? Okay. So maybe I'll start with probably very naive question. So when you added the PEG to the last system, like, was there any like reasoning to add it, or was it just like screening of what we can possibly change and see if there is anything happening?
Yes, I not showed this result because not a final one. We are not sure because we make a biotoxicity. So we put some our nanoparticles inside the body of animals, and we observe where our nanoparticles will accumulate. So the people would assume that they have not a very good result, and they are not sure that our nanoparticles without PEG are as good as we want to use in the clinical application. So they decide to add the PEG, which could make them more biocompatibility than the first one system. Yeah, but in my point of view, the system is worse because the relativity parameter, even though it's still high, this about 12 or 15. This is quite high, but it's worse than the system with PE. So yeah, there is a reason that we still have make our system better and more useful, especially for the some biomedical application.
Okay, thank you. So anyone from the audience? Students are very encouraged. Let's wait a moment.
So I have one question, because you said in the end that in the new contrast agents you have less gadolinium compared to the traditional one, and how much less is it comparing to the classical ones? Because maybe I miss it.
It could be. Okay, I try to show it because here will be the best example of it. Oh, here we could use a very low amount of gadolinium. So we have 0.08 millimoles. So this is a manganium, but this is we could put the same to the gadolinium, and we still have a very nice T1 weighted images. Normally we have some concentration about at least a half of millimoles. So I think it's 10 times lowest concentration. It will be okay.
Okay, thank you.
Okay. Do you have any other questions? Let's give it a moment. Okay. Looks like the audience today is very shy. So, okay. So I'll switch to the information about the next seminar. Just like we'll switch off your screen. Stop. Okay, so the next seminar will be in a quite long time because we have a break for the Polish NMR meeting and the Christmas break. So the next meeting online will be on the 14th of January. We'll have two talks, one from Gabriela Szczupaj from University of Warsaw and the second from Piotr Klukowski from ETH Zurich. And I hope I will see you all on the 5th of December in Warsaw. So thank you very much for joining. Thank you our speakers for giving their wonderful talks. And goodbye.
Thank you. Bye.
Thank you. Bye.